and today we have Dr. Hilary Dugan from University of Wisconsin-Madison. Dr. Dugan is an assistant professor, like I said, at the Center for Limnology at the University of Wisconsin-Madison. And as a limnologist, Hilary studies how terrestrial and atmospheric changes, such as warming air temperatures or land use patterns, alter biogeochemical fluxes and aquatic processes in lakes. Her research balances field-based programs, which rely heavily on sensor networks, with the use and development of analytical models and the application of geophysical and geospatial tools. Her research focuses on temperate and polar lakes, with sites spanning from Wisconsin to Antarctica. And with that, I will turn it over to you.
Thanks, Chris. Happy to be here. I feel like this is a good day to give my talk because the Badgers are playing the Gophers in women's hockey today. So I feel like, which is the only sport that matters. So I'm decided today I'm going to talk about some of the research that I do on road salts. I think it's a topic that is of interest to you in Minnesota, as well as obviously us here in Wisconsin. Decided between that and talking about some of my work on winter limnology, which was also of interest to you in Minnesota, but settled on road salt. So today I'm going to talk on that topic and share some of my research on that, and thinking about the impact that road salt has on our freshwater ecosystems. Can't open a newspaper, open Twitter in the winter without seeing something about the impacts of road salt in the environment. These are a lot of headlines from newspapers, public radio, thinking about what road salt is doing to our environment. And usually when we're talking about the environmental impact, it's often thinking about fresh waters, because road salt dissolves in water and everything we put down on the terrestrial landscape is going to end up in our streams and lakes. And we're not oblivious to this. We see it all winter. Starting, this time of year, that first snowfall, we see sort of piles of road salt lying around. And oftentimes we'll see images like this where, this is unnecessary, sort of excessive use of road salt. And this isn't really doing us any public safety service. It's just going to end up in the nearby waterway. And it's hard to not think of this as just pure pollution at that point. We think about the fact that we're mining road salt, ship it to Wisconsin, Minnesota. We dump, millions of tons of it on our roadways. That causes infrastructure damage, it causes environmental damage, and then eventually it flushes downstream. And in some ways, it's a little reminiscent of burning coal, where we mine it, we burn it, we release things like sulfur dioxides and nitrates to the atmosphere. They cause acid rain and cause also infrastructure and environmental contaminant damage. And so there's sort of some similarities there when you think about it. The problem is that we don't often think about road salt as a contaminant of concern the way we do other pollutants. And it's maybe no surprise to those of us who stop and think about it that seeing marine organisms in freshwater environments is not actually a mystery. It's very obvious that when you salinize water, organisms that are adapted to marine environments will happily thrive in these new habitats, obviously to the detriment of any kind of natural native freshwater organism. So this headline from Toronto, Canada, not a mystery. The rivers are very salty because of road salt. Brings up the question, why is salt such a pervasive pollutant? A couple of reasons. It's effective. It depresses the freezing point of water pretty efficiently. It's relatively cheap. There's not many substances you can buy a ton of for $70. And we think about it as a sort of a natural substance. This is not a synthetic chemical. We are mining this from the ground, and we eat it. So how bad can it be? And, in some ways, again, kind of like coal, we mine it, it's cheap, it's effective, but it has some downsides. And those downsides are that, every ounce that we put down on the ground is ending up in our soil and our water. Nobody picks up road salt, right? Like, it's not like we put it down and we collect it somehow. It is all being dissolved eventually. A lot of that shows up in our water immediately. A lot stays in ground, in sort of shallow groundwater in the soils, and sort of eventually will be flushed away. And we put down about 23 million tons a year in the United States. And that's, every year. And so since we started heavily salting our roads in the 1950s, 60s, that cumulative tonnage of salt is kind of astronomical. And the problem with salt is that we need fresh water. We need it to drink. We need it for industry. And we want to protect our native organisms that have evolved to live in freshwater environments. We also need to keep their habitat fresh. The chloride constant, so often, sort of scientifically, we look at chloride as an indicator of salt pollution because it is a common anion in most of the salts that we use. So most commonly we're using sodium chloride, but we also see use of calcium chloride and magnesium chloride, and tracking chloride as a conservative anion is a pretty easy way to track salt pollution, slightly easier than tracking cations because they're more prevalent. They also get retained in soils more. And the background chloride concentrations in Wisconsin, Minnesota are very low. A lot of lakes naturally would have chloride concentrations that are well below 10 milligrams per liter, on the order of maybe 1 milligram per liter. To give you a reference, the ocean is about 19,000 milligrams per liter of chloride. And humans are actually pretty good at tasting salts. And so the total dissolved solid limit for most drinking water standards is about a total TDS of 500 milligrams per liter. And that's mostly for aesthetic effects. We don't really want to drink salty water necessarily, and it can be harmful to our health as well. Thinking about especially sodium as an ion that can cause problems, especially people with heart conditions. So big downsides when we start to salinize water. Eventually, if we don't have any fresh water, we die, animals die, we need fresh water. And, thinking about salt as a pollutant kind of ties into this idea of some allowable level of pollution. So humans have long treated waterways as, sewage pipes. Basically, we can pollute them to a certain extent, and that pollution will flow downstream. And this is sort of a defining feature of environmental governance. I've been reading this phenomenal book by Max Lieberman, who's a professor at Memorial University, which is a book entitled Pollution is Colonialism. And it talks a lot about pollution being this basically property, right? It's like, yes, we are allowed to pollute the environment to a certain extent. And that Max's research is focused on plastic pollution, but salt can kind of be thought about in the same vein, in that we've not considered salt as a pollutant, but when we do, we're trying to figure out how much we are allowed to pollute. And so these thresholds are a feature of a lot of different regulatory agencies saying that, yes, we can put down salts as long as we stay below certain thresholds. And so these are the toxicity thresholds from the US EPA, the Wisconsin DNR, and the Canadian federal guidelines. And you can see that they kind of have a large range. These thresholds are determined usually from laboratory experiments where they put different organisms in tanks, add salts, see when they die, see when they start having reproductive issues, and then take some sort of average. And so there's, in terms of the acute impacts of salt on organisms, it's a range, There's certain fish species that are seen okay at pretty high salt concentrations. There's other species like reptiles and amphibians and freshwater mussels that are impacted at very low concentrations. And so these thresholds really are some kind of average, and shouldn't necessarily be thought of as sort of some kind of switch that we hit, that like when we surpass these thresholds, it's bad. It's really a spectrum. As we add more salt, we're stressing out organisms that are trying to live in those environments. And what's remarkable is how little salt it takes. So to hit the threshold, the EPA threshold of 230 milligrams per liter, takes about 1 teaspoon of salt in a 5-gallon bucket of water. And so I often, when I'm teaching this in class, I have my jar of road salt and ask students, how much salt it would take to actually pollute water. And 230 milligrams per liter is, 230 milligrams of salt is, maybe this much salt. And so it doesn't take a whole lot to reach these thresholds, especially considering that we often just dump piles of it everywhere. So it's obvious to see why this has become a problem. Brings us to how much are we actually using? We're using a lot. This is a great study out of Minnesota that was published a year or two ago, looking at different sources. Road salt, obviously the elephant in the room, biggest contributor to total salt use in the environment. This is probably an underestimate because it's just public supply, and so it doesn't really account for any kind of private applicator. So a lot of parking lot use, things like that. But there's also a significant contribution from water softeners, something that we have an issue with here in Madison. Most people have water softeners, and that contributes a lot of salts to the wastewater treatment facility, where they're not removed, as well as agriculture. So we have synthetic fertilizers, the use of potash, potassium chloride, as well as livestock excretion. So definitely we think about livestock excretion being a problem for other nutrients, but it does contribute some salt load as well. And if you're farming on sort of a massive scale, then it adds up as well. And Wisconsin and Minnesota are pretty similar. So that bar chart I just showed for Minnesota is probably spot on for Wisconsin as well. In terms of road salt, we use about 500,000 tons per year. And it costs about $70 a ton. I think it's closer to 80 this year. And that's relatively cheap per ton, but when you use 500,000 tons, we're talking about $80 million of total annual expenditures on road salt. Those annual expenditures are about a third just buying the salt, a third taking care of equipment, and a third paying people to apply it. So when we think about using less salt for environmental reasons, if we use less salt, we actually save a ton of money as well. Minnesota is almost identical, but 500,000 tons, 400,000 tons of road salt as well. Higher total annual expenditures, could be that you pay your employees more. But these are significant budgetary concerns for the Department of Transportation in both of these states, clearly. And the cost of road salt is only going up. Neither states have natural deposits of salt, and so we are both importing salt from other states. And all that has to be brought in on trains, shipped across the Great Lakes. It all costs money to get that salt here, which is why it costs a lot and why that price is going up. And the result of this sort of, if we actually just look at what's happening to our lakes and rivers, is that we see these massive increases in chloride concentrations in rivers and lakes, primarily in the winter. And so this is data from the city of Milwaukee, the 3 urban rivers in Milwaukee. We can see that in the winter, concentrations in a couple of these rivers sort of routinely pass those EPA, always surpass the EPA chronic toxicity threshold at 230, but also are routinely passing chloride concentrations of a gram per liter. which is some people's definition of the delineation between fresh and salt water at 1 gram per liter. This is an example of a storm sewer here in Madison. This is electrical conductivity, not chloride, but what it shows is that these concentrations, during these February runoff events are sort of halfway to ocean water. So these storm sewers are brackish, if not considered to be brine. And that's in Madison, these are flowing into our urban lakes here. And the result of that is that we see chloride concentrations increasing. So these are the Madison lakes. Madison is sort of like the Twin Cities, where there's a lot of water right in the city. And we're blessed here with having long-term data collection. And so we know that in the 1940s, the concentration of chloride in these lakes was close to 1 to 2 milligrams per liter. And it's just increased since then, pretty steadily. The 2 larger lakes here, Mendota and Monona in blue and red, they've been just steadily creeping up in chloride concentration over time. Lake Wingra in yellow is a really shallow lake. Its watershed is 100% urban. And so it varies a lot during the year, but it too is increasing. And none of these systems show any sign of decreasing or leveling off yet, unfortunately. So kind of unclear the trajectory of where these are headed. Lakes in the cities have at times had much higher concentrations than these. They're smaller. And the Minnesota Pollution Control Agency has actually done a really good job at curtailing those, and actually do see some decrease in concentrations there, just because the concentrations were so incredibly high at one point in time. So if we look at the states together, anyone who knows the geography of this region knows that all of the hot spots for chloride on this map correspond with urban infrastructure and agriculture. So the urban areas of Milwaukee, the Twin Cities, Madison, Green Bay kind of pop out on this map, as well as the opposite being, the North Shore, Boundary Waters, Northwoods of Wisconsin, having concentrations, virtually, so low that we can barely measure them in some cases. So it's pretty obvious just from looking at this map, sort of what is causing these salinization problems. And not only do we see that in surface water, but we see it in groundwater as well. And so the wells here in Madison who drink groundwater have an increase in chloride as well, because they're receiving surface water. And so this is another area of major concern, thinking about the costs associated with drilling new high capacity groundwater wells. So we can look at maps, we can look at the data and see that this is a problem. But there should probably be some more scientific rigor to that, other than just plotting a map. And so a lot of work I've tried to do in the last few years has just been thinking about how widespread of a problem this is. And so this was a paper that we had come out in 2017, looking at long-term trends of lakes in North America. It actually started as a paper that was comparing North America to Europe, which I thought was really interesting. The reviewers didn't, so it ended up being a paper just on North America. But what we show in this paper is that most lakes in the what we call this sort of lakes region of the Midwest, Northeast, and Ontario had either increasing trends associated with impervious surfaces, or there was no trend. Very few lakes were decreasing in chloride concentration. And so again, these sort of stand out in urban areas. A lot of these lakes in the Adirondacks, not much change in these sort of protected habitats. More recently, worked on a paper with a couple of grad students here in Wisconsin, looking at the watershed for Lake Michigan and comparing water quality samples taken in 2018, which is on the left. So this is like a circumnavigation of Lake Michigan, sampling as many tributaries as possible, versus long-term data from the water quality portal on the right, looking at sort of what the chloride loading is to Lake Michigan. And again, these sort of hot spots of, Milwaukee, Green Bay, Indiana really stand out. And really it's just, the largest watersheds are the contributors of chloride, just because they're bringing in so much water at the same time. And this is a way of trying to understand trajectories. So, if current practices stay the same, what will we expect in the future? And for a lake like Lake Michigan, where the lake is huge and the watershed is proportionally kind of small, given the size of the lake, if current trends stay the same, chloride concentrations will increase, but probably only to 25 milligrams per liter or so, because the lake is just so, there's such a huge dilution effect from the volume of water and, just the amount of precipitation it's receiving. But if we look at the individual tributaries, and this is a random forest analysis, what we saw is that, like almost everywhere, the biggest driver of chloride concentrations in the tributaries was impervious surface and population density, urban landscape, followed a bit by agriculture. And we can do that same type of analysis on a much larger scale. So this is the sort of a region of the US that uses a lot of road salt. And so this is a 17-state area, contains about 23% of the lakes in the US, particularly reliant on road salt application. This region uses millions of tons of road salt. And we mined the water quality portal for chloride data, and we're able to find about 29,000 observations. Clearly not a spatially distributed sample. Certain states have done a much more thorough job at both recording chloride, but also contributing that data to public repositories. So it's, some of these other states might collect data, they just might not have it posted publicly. So this is, clearly there's states that are missing data here, but probably similar trends to other states. So we can take this data from 29,000 or from 2,700 lakes and use that data to try and look at the drivers. So again, another kind of random forest analysis, saw that low and medium development and agriculture, again, kind of come out as these top drivers of high chloride concentrations. And so what that has enabled us to do now is if we can understand the drivers, we can then sort of map that pattern onto all of the lakes in this region. So that's what we did. We tried to predict chloride for 49,000 lakes. And what we saw were there, a lot of lakes still have probably very, very low chloride concentrations. And that's because they're in watersheds that have really not been developed. So that's fantastic. That's good news. And it's really only sort of a small handful of lakes that probably are at really kind of high risk for salinization. And, they map onto, again, kind of those obvious urban areas. This is sort of our predictive map. And we can narrow it down to lakes that have chloride concentrations that are, in this case, just thresholded to more than 50 milligrams per liter of chloride, which again, kind of an arbitrary number, not biologically chosen, but just a definite indicator of some kind of concentration that is much above what you'd expect from a natural concentration. So in this study, we found that most lakes probably have chloride concentrations that are still less than 20 milligrams per liter, and only a handful are at sort of significant risk at the moment. Although, as these trends continue in terms of our current practices, we are just adding more salt to the landscape. So that's, that risk is going to continue into the future. But this enables us to at least, if we're thinking about managing systems, highlight systems that, we should be monitoring to make sure that we aren't sort of surpassing some of these concentrations. So what does this mean for lakes? Like, yes, we now know where this, like how widespread of a problem this is. We've sort of understand the drivers well enough to make very educated guesses as to where problems might be occurring. So what does that mean for lake ecosystems? It has a lot of impacts, and I don't have time to go into all of them today, nor do I have necessarily the expertise to go into all of them. But it has impacts on lake physics. Salinity changes water density, which has a really important control on mixing dynamics. As limnologists, we're often not necessarily trained in thinking about salinity on lake mixing, because traditionally, in freshwater systems, it has such a little impact. But as we start increasing the salinity of lakes, then we have to actually start considering salinity as a driver of hydrodynamics, kind of like oceanographers do. Also, inherently, salinity is going to change lake chemistry. I mean, it is, a chemical. It is a chemical that we're adding. But there's been a lot of work looking at sort of the associated chemical feedbacks with higher chloride concentrations. So in terms of weathering dynamics, chloride can liberate other ions, is good at liberating heavy metals from soils, also from drinking water pipes. And so there's other contaminants that might sort of come along with increasing salt concentrations. Also might change your cation concentration given just sort of cation exchange in soils with sodium and those divalent cations. So there's sort of lots of interesting chemical feedbacks as well. And then of course, this is going to have an impact on biology. We have freshwater organisms that are adapted to freshwater. And as we increase salt, it's going to cause problems for osmoregulation. And that's going to impact different organisms differently. And that might have, cascading influences on trophic dynamics. And so there's lots of open biological questions on what freshwater salinization means for lake biology. So I'm going to give just an example of one attempt at sort of tackling the question on physics that a postdoc of mine led this past year. So this is a paper that just was published this year in LNO Letters, thinking about the impact of winter salt concentrations having impacts on lake stratification and mixing dynamics. And the fundamental concept here is that in the winter, you often have inverse stratification under lakes due to temperature. And so you have a water column that has a density gradient, with the bottom water being slightly warmer because it's more dense. And it's weakly stratified. And so when the ice comes off in spring, wind usually mixes the lake pretty easily. However, if you have the same in winter, salty water sort of coming in the river, that inflowing salty river water is going to be more dense, flow to the bottom of the lake. And so the bottom of the lake and the hypolumian might increase in salinity in contrast to the sort of fresh surface water. And so if you have this salt gradient in your lake, that's going to add to your density gradient, creating a greater density stratification due to salt. And when the ice comes off in the spring, it's just going to take a lot more energy to break that stratification down. And so you need greater turbulent forces to overcome that stabilizing force of salt. And so that might, in effect, kind of delay spring mixing, because it takes more time to break down that stratification gradient. So that's sort of the concept. And we tested this concept in 3 ways, using the 2 lakes in Madison as examples. So we one used in situ observation. We put in electrical conductivity sensors and temperatures sensors on a lake buoy under the ice in 2 winters in both lakes. We lost the Lake Mendota buoy the second winter. So we only have 1 year for Mendota, 2 years for Mendota. We also tried to attack this question analytically, looking at stabilizing versus kinetic forces. So try to answer this question mathematically. And then also looked at this numerically using hydrodynamic lake models, so process models, where we calibrated models to the lakes and ran salinization scenarios. So it was kind of fun to have this three-pronged approach to answering this question of what impact would salinization have on these lakes. So this is the observational data that we got back from the buoys that we deployed. So the left is Lake Mendota, the right is Lake Monona. The dashed lines are lake ice freeze. So when it freezes in the winter, followed by when it breaks up in the summer. And that is the same for all three of these panels. The red line is electrical conductivity. So what we see is that, then this is electrical conductivity at the bottom of the lake. We see that conductivity increases in the bottom water, either as soon as the lake freezes in the winter, in the case of Monona, or slightly after, increases throughout the winter. When the ice comes off the lake in the spring, what we see is that conductivity gradient isn't immediately mixed. It actually, there's a delayed mixing. And so in all of these cases, EC doesn't go back to sort of pre-winter levels, so which we consider to be full mixing, until a handful of days or up to a couple of weeks in the case of Monona this year after ice off. So what we're seeing is that when ice comes off, the lake doesn't immediately mix, even though in all of these cases, the lake is isothermal. So the surface water temperature, the light blue line and the dark blue line, the bottom water temperature are the same. And so what we see is that we don't have thermal stratification, but we do have salinity stratification, and that is delaying that spring mixing. And so it's not until a few weeks after ice off, usually during a big wind event, that we finally get that stratification breaking down. So we do see this having a delayed impact on stratification, on mixing, we think. Also looked at this analytically. And so there's, if you look at the paper, there's sort of derive how we're looking at this critical amount of salt that in theory would prevent mixing. And our results were that for these lakes, it would be around 1.3, 1.4 grams per kilogram concentration in the bottom water that would prevent mixing. So this is a concentration that is, we're not coming close to that concentration yet in these lakes, but it's not unreasonable that other lakes that are smaller, more impacted by salt runoff might. And then we also used a process model. So this is using the general lake model. We used Lake Ensembler, which is a ensemble package, but this is just one model where we allowed river water to be saline in the winter at different salinities. And this is an example of that salinity being 1.5 grams per kilogram. And this model shows that kind of salinity is building up in the hypolimnion. Over the winter, ice comes off and it takes a while to kind of flush that salt out of the hypolimnion. So we turn salt inputs off in the summer. And we can then use these simulations to look at something like first mixing day of the year. The gray dots are the null runs, so sort of current concentrations. The darker the red, the more saline that simulation is. And so we see that the more salt that's coming in, you sort of delay that first day of mixing. And if you increase the salt enough, you actually stop spring mixing and the lake doesn't mix until the fall. And so you effectively go from a dimictic lake to a monomictic lake. It's only mixing in the fall. So example of physics. So, what's next? I think there's a lot of sort of interesting limnological questions to be asked, also management, conservation questions. A big one is the biological function. What have we seen and what will we see in terms of shifts in communities in lakes and rivers as chloride concentration increases. So there's some evidence that you shift phytoplankton and zooplankton communities with increasing concentration, and unfortunately, it's towards cyanobacteria and maybe other phytoplankton communities that we would prefer not to have. Shelley Arnett's group published this great paper this year looking at the impact of salinization on zooplankton, and her group cultured Daphnia species in a soft water culture. So this was Daphnia from soft water lakes, so very low natural ion concentrations. And their results showed that Daphnia were very sensitive to salinity at very low concentrations, so between 5 and 40 milligrams per liter. So those are concentrations that are much lower than those government thresholds that I talked about earlier. So the EPA is being 230 milligrams per liter. Well, this paper is showing that you're significantly changing your Daphnia species at concentrations at more like 10 milligrams per liter. This study was on a soft water lake with naturally low ion concentrations, so probably would see different results in hard water lakes. But that shows that we probably shouldn't have these thresholds that are applicable to like all lakes in the entire country when there is this type of sort of natural variability in what species are adapted to. There's also interesting work going on thinking about evolution and adaptation. We have been salting lakes for 80, 70 years now. And over that time, likely have seen evolved traits to potentially deal with sort of higher ion concentrations as well. So lots of sort of fascinating biology to be asked. In terms of, what we should be thinking about as sort of advocates for less salting. So, wearing our scientist hat, but thinking about management and advocacy. This is a problem that can be solved. Salt stays dissolved in water and eventually will be flushed out of systems to the ocean, which is why the ocean is so salty. And what we need to do to reduce salt concentrations and protect the freshwater environments is we need to use less salt. Like, it's a very easy answer. Using less salt is, challenging, but considering that we probably greatly overuse salt at the moment, reducing it should be pretty straightforward. Eliminating it will be much harder. But there's lots of sort of policy options thinking about, everything from just grassroots organization to regulatory agencies actually treating salt like a pollutant, to sort of curtail our salt use. I do a lot of work with the Wisconsin Department of Transportation, and they're actively trying to reduce salt, from an environmental point of view, but also from a budgetary point of view. This is a huge cost to our state and local governments. And so if there can be cost-effective measures that also benefit the environment, it's kind of a win-win. So we're seeing a lot more brine application here in Wisconsin, which is saving a huge amount of road salt. So that's coming from a public agency that has is invested in this. But at the same time, we have lots of private application that's unregulated. You can put as much salt as you want on your driveway that washes into a storm sewer without, any ramification. So, we definitely have to just start thinking about salt as a pollutant. And I think people will start acting differently, hopefully. And so going forward, I think this is going to take just a different way of thinking about salt in the context of it being a pollutant and not just sort of a natural chemical that isn't causing any problems to our environment. So I'm going to stop there and happy to take questions. I like to talk about this. So yeah, looking forward to sort of chatting about some of your thoughts as well. So Thank you.
Awesome. We have some questions in the chat already for you.
Great. Yeah, so I'm just going to go in order, I guess. So one of the questions was about the map showing that you can kind of see I-94 stand out. And is that a sampling effect, convenient of access, or an actual effect? Probably both. They're, every time I've sampled lakes beside an interstate, they are salty. And you actually can see some pretty interesting effects too from groundwater flow passive. Like often you'll see lakes on like one side of a highway being a lot saltier than the other side, just depending on where your flow paths are. So sometimes convenient to sample. Also, sometimes lakes beside highways are incredibly difficult to sample because you can't pull over on the side of an interstate and sample things very effectively. So probably a combination, but yeah, there's a lot of salt applied to interstates, and that is all running off. So let's see. So a question about thresholds and how open regulatory agencies are to thinking about different thresholds for lakes and moving the needle away from one size fits all regulation. Yeah, so that's a great question, Gretchen. I think agencies it's on their minds. Michigan recently has been thinking about, and I don't think they had a state chloride threshold. I think they were using the EPA's, and they've been thinking about setting their own. And the number they're aiming for is much lower than the EPA's. And so there's people are working on this as an onlooker, realizing that setting these thresholds is probably agency specific and how difficult it would be to change some of them. But yeah, states are aware, and I think I don't envision Wisconsin changing theirs anytime soon, but especially states that don't currently have one are looking at different numbers. So we'll see.
Yeah, I'm just gonna chime in really quick, Hilary. I think it's so interesting, a little bit of a tangent, but like, you and I both work on like big landscape level lake stuff, and we're like, oh, every lake is different and we need to like understand the variability. But then like I said in the comment, we saw in Minnesota, like the state agency tried to set a non one size fits all regulation for sulfate, something different, but it was shot down by a judge who was like, this is too confusing, I don't like it, take it away. And so it's just an interesting intersection of like policy and the science that we do, and might be worth following up on how we might do that better.
Yeah, Shelley, and I really like Shelley's work on the saltwater lakes. It's just a really obvious example of how your background, your total background, just total dissolved solid is obviously going to impact how much chloride's also going to impact that, because if you're, it's kind of relative to the total proportion. So
right.
Yeah, especially in our states that sort of straddle geological divides, and seeing a big difference in just sort of natural concentrations as well.
Mm-hmm.
Let's see. Have you looked into potential impacts of the cyanide compounds added to road salt as decaking agents? I have not. Obviously, another contaminant of concern. Yeah, there are definitely additives to different road salts, and if you have cyanide as a decaking agent, it's hard to it's hard not to assume that that's going to have environmental impacts as well. But it's something that I haven't looked into much. Question about Europe. We did a lot of work trying to look at European management approaches, as well as sort of observational trends. In one place that linologists often look to is Sweden because they have a lot of data on their lakes. Also a snowy country that has a lot of ice on their roads. And what we saw was that the road salt is used very sparingly, if not at all. And that is it's just cultural. It's just an acceptance of like, yeah, roads are going to be snowy and icy and we can't drive 70 miles per hour on them in the winter. And so they've just never had this approach of clearing the roads immediately when it snows. For a long time, the Midwest had sort of a clear roads policy, like we are going to remove all ice and snow from roads everywhere. And that just culturally like wasn't the approach. And so they just historically haven't had the quantity of road salt applied. It's used in very specific locations. And also they have much stricter regulations on private applications. So, it's public agencies, will use it when necessary, but it's not like you can, people just go out and buy it and use it. So it's a very different approach and results in salinization not being a problem. Scandinavia, a lot of the major cities are also coastal. And so you also have arguments, and this happens in the US as well, where municipalities will argue that they're, if it's a coastal city, the stormwater runoff is just going to the ocean, so it doesn't matter. And there's a long history of arguments about that in Puget Sound in Seattle, if anyone's curious about local arguments. But there's something to be said for that too. Like if you're not polluting freshwater environments, then then your problems come down maybe more to infrastructure damage and things like that. Does Wisconsin have any plan for the use of dirt instead of salt on roads in the winter? So there is more, there's use of sand as an aggregate for traction, and that is common. The DOT uses a lot of sand in the winter. They still salt roads in northern Wisconsin, but they do have temperature thresholds. So if the temperatures are below, 15 Fahrenheit, sodium chloride isn't all that effective in melting ice. And so as you get to colder climates, so northern Minnesota, you start seeing less salt use because it's just doesn't do anything. And at those colder temperatures, you also don't have as much ice. So, where you get really icy conditions are these climates where you routinely freeze thaw. So, maybe it snows during the day, or maybe it snows, the sun melts the snow into puddles, then it freezes at night and it creates ice. And so, we tend to just see less salt use as you go further north. But, will that be the same in the future as climates change? Also kind of unknown as well. But in this region, which is naturally sandy, the use of sand doesn't seem to be an environmental problem. There are places where increasing turbidity can be a problem. And so it seems okay. And, something that at least here in Madison, you commonly see just sand used on kind of like the side roads. Let's see. So the use of sand, again, there's no chloride in it, there's no salt, so it's not, won't have the same impact. There's alternative solutions. Some of them, you can buy sort of other types of de-icer. A common one that you'll see now are acetate solutions, which seem to have less environmental impact, but also are used at a very small scale. So it's hard to imagine there being any alternative solution that you can use at the scale that we currently use salt at that would be as effective, and definitely nothing near as cheap. And so the part of the issue is there's no obvious alternative. There are some interesting engineering ideas down probably well into the future. Things like, the advent of permeable pavement will definitely decrease ice because you won't have water freezing on the surface if you can drain water through pavement. So permeable pavement would be much more effective than sort of current road surfaces at preventing ice formation. There's also places that have started experimenting with solar heating. You see on some bridges, some places now, where they're using solar voltaic cells in pavement to heat roads and keep them from freezing. So really cool, some really cool engineering ideas like that might prove successful in the future. But no sort of alternative kind of chemical addition at the moment. All right, I think I've exhausted the question list.
Awesome. I have a quick question as well. So I was wondering if you knew of any like terrestrial impacts, kind of as salts being aggregated in the area or something like that.
Yeah, I mean, there's been a lot of work looking at sort of just trees in ditches, and they are impacted. You often see a lot of just like tree and plant death along the sides of roadways. Yeah, that's a problem. Salt will also change the physical structure of soils too. So you can get kind of just soil changes as well that will have impacts on, plant rooting. So there are obvious terrestrial impacts as well, and probably a lot that we haven't considered, as well. So yeah, not just water. Oh, neat. Someone messaged me about Minnesota DOT trying to prevent shadows on pavement resulting in ice buildup. So other mechanisms for using the sun's power to melt ice. It's cool. All right, well, there's no more questions. I think I will leave you with, if you see piles of salt this winter, don't hesitate to go in and voice concern to the property owner. They love it when you knock on business doors and ask about private application of road salt.
We do have another question in the chat now.
Yeah, climate change and snowfall. It's sort of an unknown. There's definitely climate change forecasts that are expecting more extreme precipitation events, which should also mean more extreme snowfall events. I think the Northeast the last few years has experienced, these huge snowstorms that historically haven't been as prevalent. All these Snowmageddon events. So maybe it's kind of unclear. Precipitation is really hard to forecast. Wisconsin had been getting wetter for a decade until this year. We've had a really, really dry year. I think you guys have too. So toss up, I don't know.
Okay, awesome. Thank you again so much. If there are no other questions, which it looks like there are none, we can wrap up. We have our final seminar next week from Dr. Bum. And that will end our fall conservation sciences seminar series. So thank you again, Dr. Dugan. Appreciate it.
Thanks, everyone.